All right, so welcome back again, everyone, for the second session. So let me start with sharing my screen. Right, I hope you all can see my screen. If you can't see, please let me know. Okay, so in this session, we're going to cover something called supervised machine learning. Just a quick question: have anyone heard about that terminology before, or this concept, supervised machine learning? You can feel free to unmute your microphone or just write on the chat. Have you heard about that terminology before? I'm sure you heard about machine learning, but have you heard about supervised machine learning? Yes, okay, from introduction, okay. Excellent. So what does that mean by supervised? Can anyone explain what does that mean by supervised, and what's the difference between supervised machine learning and unsupervised machine learning? Can anyone explain that? Yeah. Supervised machine learning has labels. Yeah. Exactly. Known items. That's true. So basically, we predict examples in supervised to train. Yeah, we provide examples in a supervised way to train. Yeah, that's correct. Right. So the supervised machine learning, as you have just mentioned, is that we based on some samples, okay, to train our model, to train our machine learning model. And in this case, we call it a supervised machine learning model in order to predict something else, which is the model has not been seen before. Okay, I'll give you a very, very simple example. Again, we've mentioned that supervised machine learning can work in text, can work in image, can work in sound, any other things. So, for example, if we're talking about supervised machine learning in images, for example, and I do have a data set of, say, for example, 10,000 images, and I've used 8,000 images of those classes, for example, a cat class. So what happens is, if I provide the machine learning with the cat, and just telling that the machine learning, okay, this is a cat, this is a cat, this is cat, and then trained our model over, for example, 8,000 images. What's going to happen after that? Simply, if I get another image for a cat that the machine learning model has never seen before, and I brought this image to the cat, to the cat image to the machine learning model, and asked the machine learning model what is that, and the machine learning model will be able to classify this image as a cat. So this is simply what we call it supervised machine learning. So supervised machine learning based on some sample or some data. So we do have a lot of different supervised machine learning. So today we're going to introduce a couple of these, such as linear and logistic regressions. Okay, so we're going to consider today linear regression, which has been used to simply solve the regression problem of for continuous output. Within the linear regression, we're going to learn a little bit more about that. Within the linear regression, we're going to fit a linear function to optimally match data between classes. Okay, and to solve a so this is a regression problem, and there is a classification problem. So classification problem is simply a generalized using logistic regression in here. So this is a generalized technique to classify, which is requires simply use to move to nonlinear function. Okay, so regression problem, I was just trying to just give you a very simple understanding here. So we do have a regression problem, the prediction, we call it a prediction. Prediction, the problem that we have here is a prediction or regression problem. So for example, you can see this graph here. Say, for example, we do have a CO2 emission, the rate of CO2 emissions, and we have here the temperature. Okay, say we have, for example, the global warming problem is because of the CO2 emissions. So if when the CO2 emission has increased, the temperature normally increase. Okay, so just simply imagine that's the problem that we have got. Okay, and we have written a regression line. We're going to know how to do this linear regression, and we have this kind of regression line here. Okay, based on the data we have some sample data. For example, we have gathered data from previous years, and we have measured the amount of CO2 and what is the data for simply for the temperature in this data. Okay, let's use other sample here. Say, for example, in 1990, the data was here. This is the data, looks like that, and you can think about if you represent the data between these two variables here, the CO2 emissions and the temperature. This is the data that we have plotted on the graph. Okay, so if we wrote a regression, if we draw a regression line, so the regression line will be something like that. So what is the importance of the regression line? The importance of the regression line is that enables us to do a prediction. That means in a way that the scientist can say, for example, if we in the future, somewhere in the future, if we reach some certain CO2 emissions, that means the temperature is going to be that kind of level. Okay, so we predict based on some previous data or some data, and we have brought a regression line or regression line, so we're able to predict. So basically, if we minimize the CO2 emission to that point, so that's going to be the temperature or something like that. Okay, and so on. So you can think about that. We've wrote that prediction. We have that kind of regression line in order to able to predict using like a machine learning or statistics to predict the future values based on one of the values. Normally we call the temperature is the dependent variable, and the CO2 is the non-dependent variable, which is the temperature is dependent on the CO2. Okay, so that's the simple problem we're going to try to solve using linear regression, which is a regression problem or prediction that we're trying to do. The other problem we do have is simply classification problem. The simple way which is going to be used today using logistic regression is to classify something. If we have data, so say for example, if we have like a patient and we would like to classify this patient if it's in risk of some disease or something or not. So this is a classification. It's either 1 or 0. Okay, based on the feature or based on the record that that patient have. So that problem we call it a classification problem. So we classify this patient either on that category or the other category. Normally it's like a 0 or 1 category. Okay, so this is another type of problem. We call it classification problem. Okay, if we go deeper for classification, for example, in the problem what we're trying to look at in the images, so we try to classify the objects. We have a number of objects we can classify. This is, you know, like a car, this is a human, this is a person, and this is a roundabout, and so on. Okay, another way of classification, if you have an image of you know, like human beings, and you can classify this male or female, for example, that we call it a classification problem. Okay, if we go deeper into machine learning and deep learning things, you can see other problems as well, such as, for example, segmentation problem. Usually in medical images, we do segmentation. So simply we do, you know, this region of interest from an image, we do like a kind of segment this part. Okay, so it's very interesting. It's very important while you looking at the machine learning, implementing machine learning or artificial intelligence technique or machine learning or deep learning in the future. So you know exactly what you're trying to solve, what sort of problems you are trying to solve. Okay, so I hope that helps you to understand different types of problems that we have got. Okay, we might see some little bit of a mathematics here, so don't worry about it at all. We, you know, like it's a simple thing. We're not going to go deeper on that. If you don't fully understand it, that's absolutely fine. Again, this is we call it a conversion course, so you don't have to have a background in mathematics or computer science in order to you know, to be enrolled and to perform in this course. Okay, so we start with the linear regression. We're trying to the basics of linear regression, which we're trying to, where you recall the linear regression problem, we are trying to estimate a function y. So this is the function y with a weighted linear function over inputs feature x1 to p1. Oh, this looks a little bit scary, but it's not really like that. Okay, so we have y hat here. We're trying to predict y. We're trying to predict y using the coefficients here, the p0, p1, and beta naught, p0, and so on, using these coefficients and the constants here and the coefficients here to predict the y value. Okay, and here we call it so we lit the vector representing the beta here, which is we call it w, and the w here is simply we call it, which is a very common name that you're gonna hear about, which is the weights. We call it the weights that we put in order to solve this problem. Okay, so the main task here is simply to find the w value, the values for w here, to minimize the difference between y hat and y. Okay, and we're going to talk a little bit more, details in here. And in order to measure the minimizing, when we say minimization or minimizing the value between y hat and y, there is a formulas, or you know, like a way to measure that minimization. Okay, and we have two ways, so don't worry about the equation that much, but we have mean square error, or MSE, and root mean square error. Okay, or simply they are exactly the same. We just you know, like we have a root square here over the root mean square error, or RMSE and MSE. Okay, and this is simply measure the difference between, you know, the difference between y and y hat. Okay, so I'm just simply just explain to you here what is the minimization and what we're looking at here in the linear regression. Okay, so say for example we have two variables here. Okay, and let's see for example, so we have CO2 here again and the temperature values. Okay, and it's not the error here we're going to see. It's not exactly a variance and standard deviation at the moment, but we're going to look exactly what the error here means and why I would like to minimize the error. Okay, so let's try to plot some data as well. So this is like a run. This is the data that we have plotted. So we say, for example, we have a tabular data between T and CO2 and the temperature, and we plot this data based on the data we've gathered. We've collected the data over the years from any agency that do that kind of data collection. Okay, and when we plot the data, we did plot the data. That's the data looks like, and we can think about this as a kind of. We can think about this, the way we represent here is a positive relationship. Positive relationship means as the CO2 emission has increasing, the temperature normally it does increase as well. Okay, so we have a kind of trend. We call it, this trend is the positive linear relationship trend. All right. So what is the linear regression here? What we're trying to do here, and how we're going to use the root mean square error or the mean square error in this instance. So simply, it's very simple. It's very, simply what we're trying to do here is to draw a line between this point, which fits the point, the best line to fit between this point. Okay, so this is, say for example, this is the line which fits, best fitting between points. So let's put some points here as well. Okay, so this is the green line. Okay, how I decide? So this can be green line here. This can be this line here, can be this line here. So there's many lines you can put in order to represent this data or to fit between this data. Okay, but the linear regression is simply the best line to fit between the data point that I've got, and the way I measure that is by using, if you think about this point here, between this point, data point here to the line, and the data point here in the line. Okay, and say for example this is a positive value, some certain value, and this is a negative value. Okay, and for all the point you can think about this is simply we call it sometimes the residuals, and the linear regression. Okay, the linear regression is simply the best line that the submission of all of these residual or all of these red lines here are the minimum. Okay, and that's what we call it, a minimize the root mean square error. Okay, and why we used the root mean square error, what's the difference between, what's the importance of the square root here, is that because we have positive values and we have a negative values here, and we don't want to, we have the negative value to simply eliminate the positive value, but in this case we trying to add all of them together. Okay, so this line here plus this one plus this one plus that, and so on. Okay, and this is for the green line, and you can think about it is basically same sort of things for the yellow line here. So the yellow line having these residuals here, and here, and so on. Okay, so the addition of this residuals or this lines here, say for example for the yellow line is some certain value, say for the yellow is maybe I don't know, maybe 10 or something like that, And for the green line is simply, we can say it's the result is value is 5. So because this is a 5 and this is a 10 and this is maybe 12 or 11, so I'm taking the minimum root mean square error value. And this line here is going to be our regression line. Okay, and the importance of the regression line, as we have mentioned in the first slide, is simply once we have the regression line, so we can do the prediction. So any point here, we can get the relative or the other point in from the x-axis, we can get the y-axis. Okay, for example, if we have CO2 here is maybe 8 or whatever, so we can, you know, the degree is 11, something like that. And we can from later on here in the if we have increased that to maybe 10, so we're gonna have maybe 13 value here, something like that. Okay, so that's simply the regression line, and we have used the root mean square error to calculate the value and to minimize the root mean square error between the data points and the actual line itself. Okay, anyone has any questions? So this is simply the remaining, we're going to be built on that, but this is simply the linear regression, as simple as that. Okay, so the linear regression has a closed form solution. So all the equation here we're trying to do is simply to I'll just gonna show you one thing here. It's a very I'll just keep it a moment. I do have here, so you can think about if you remember a graph, so we can see if you have y equal x, so you have a line like that. If you have a y equal 2x, so this is the coefficient or the value here. So so we have so you have the value here like this way. If you have 2x plus, so the 2 here is simply the angle. In this case, if we have 5, so you can see the angle is bigger, or we have 1, something like that. If you add 1x plus 2, 2, for example, so you can, this line here has been up by 2. Okay, so this kind of you know, like this kind of line, and if you have, and this is why we call it a linear you know, like linear relationship or linear equation. Okay, if we have x to the power of 2, for example, so that's basically moved to another another non-linear relationship. Okay, but all what we're doing here is basically simply a linear relationship. Okay, and this is a representation of you know, like the value of this coefficient and how these value affect the line that we have got here. Okay, Rosaline, please go ahead. Rosaline, if you raise your hand. Go ahead if you have any question. Right. So are there function or library that calculate honestly? Yes, that's a good question that we was about to I was going to mention. So you don't have to worry about you know, things such as root mean square error or mean square error or even linear regression. So we do have a lot of packages that already implemented, and by the end of the session we're going to go through one of the implementation of linear regression and logistic regression as well. So we normally use already existing packages. These packages has been implemented in a very good way, and packages such as scikit-learn or any other packages, you just call the functions or the function that you need to do, and that's going to be done by itself. So you don't have to really code everything from scratch. in here, and that's very useful for us as in, you know, like a machine learning, working in machine learning or AI in general. Okay, good question. So in terms of the linear regression, as we just mentioned, is simply we're trying to calculate the weights. What's the weight, which is the coefficients in this case. Okay. Directly solving is expensive. If you don't, you know, don't bother yourself about this one. But this is about the you know, like the big O. We call it big O. If you have heard about it, it's simply how complex something is computationally. Some software companies interviews, they ask, for example, the candidates to write software, and they measure the complexity of the software by the big O, for example. They would like them to write a more efficient software programs. So the more efficient software programs, they basically use less computational than the other software. So you can use some sort of data structure, for example, bubble sorting things before you do your some sort of operation, which is affects the complexity, right? So yeah, this is what we call it, the big O. So this is the complexity for the multiplication and for the inverse, right? So example of linear regression, it's as you just asked it right now, it's very simple. So we have a linear regression function. Of course, there's some packages. We're going to have a look at it at the end. So there's some packages we're going to you know, like look at. So we just call linear regression function, and this linear regression, we have it as a RGR or regression or regressor. And then we have a method called fit. This fit is simply, and we pass the data, the X, Y data here to the regression model that we have got. And fit here, you will see this method, this word a lot. Fit means like training the model. So we fitting the model and training the model, we call it, we use this this method fit in this case. Okay. Here we just scatter plot. So this type of plot, we call it a scatter plot, and we simply plot the values on the scatter between X and Y. And we simply, after that, we plotting the regression line. The regression line is the red line here. And as we mentioned, it can be more than a line, but this is the best line, the best fitting line based on the data that we have got. And this is simply the regression line we have received. Okay, and this is simply the data that we have. I mean the part of the code to simply write the regression line, and the regression line, the simply we used the main function is y equal to x times 3 plus random factor to generate the data. Okay, and the best, and if you remember that we have mentioned that with the aim is to get the coefficient, and this coefficient, in order we use this coefficient to draw the line. So the best coefficient based on the linear regression that we've got is 1.9 and 3.1, which is very close to 2x plus 3 in this case, 3.1. So this is the best regression line that we have received. Okay. Do we test the data before regressing like in econometrics? So that's again a good question. So there is data. I think you have and you know, like you've been introduced to little bit slightly to it in the morning. So you need to do some sort of data cleaning and data pre-processing before performing any machine learning models, okay, such as linear regression or logistic regressions or whatever. Okay, so you need to make sure the data is, you know, you don't have any outliers in your data. Your data is complete and clean. Why is that? Because if your data is not clean enough or good enough, so the model will not perform well, or you will having a model that's simply not accurate enough. Okay, so that the way of testing the data is simply we call it like data clearing and data pre-processing before performing any linear regression. And the way you think the testing the data is by clearing and pre-processing is there's something called data exploratory analysis, or DEA. This is something you will be introduced to tomorrow in tomorrow morning session. The DEA analysis is before performing any regression or implementing any machine learning model. You simply visualize the data, see if there's any outlier or how the data looks like. So you do some sort of initial testing or initial visualization visually, and initial checking for the data before you perform any machine learning model. Okay. Can we do interpret? Yeah. So interpretation, you can, this is decision that you can do data interpretation or any sort of data pre-processing. It's a part of the processing that you can perform, and you need to understand the data and perform that. Again, this is an initial stage of the preparing the data, you can say, before performing any data modeling. Okay. Any other question? Anyone has any questions? All right. Excellent. So I hope that this example is clear for all of you guys, and this is actual implementation. This is how we implement a linear regression using simply using Python, and we can implement that in Google Colabs, for example. Okay, so all that done by linear regression. So you just this is the intercept. We call it the intercept and the coefficient. Don't bother about that much, but simply these are the two things: the W's values that we are looking at, which is the 2 here. The coefficient here is the 1.8, and the intercept is 3.1. Okay. Can linear regression be done for data that has more than 2 columns? So the number we've got here is basically the features. Yeah. So so the features we're going to mention later on. So the mapping the feature is not 2 columns, but I will give you an example. Okay, say for example you do have a car. You would like to predict the car price based on some of the feature. Okay, and this feature can be, for example, the age of the car, can be the for example, the car model, maybe the cylinder, maybe the speed. All of these are feature, and all of these feature can simply used within the linear regression model to predict the car price, for example, the price of the car. Okay, so you can build a model based on the previous data for sold cars, how much, the specification and the car that's being sold, to build a model to predict the car price. And probably these kind of, of course, this modified things, but people, companies such as, we buy any car or things like that. So most likely they're running a machine learning model to to predict the car price. And this is one of the things that you probably not can't see it, you cannot look at it in notice it, but you will see after finishing this course, you will find a lot of things around you using machine learning and AI as a tools to help you. One of the things here, when I record here, you will find my my voice converted to text. Again, this is machine learning. This is AI things. A lot of things, recommendation things. And if you go for Amazon, like product recommendations. If you YouTube, prediction recommendation for the next YouTube video or whatever. All of that, everything, all of that is being used machine learning models to do these kind of all of these recommendations. Okay, yeah, so the answer to your question, yeah, you can use a number of features in your data to use your model to predict. Okay, one of the important things, but we're probably gonna learn later on. So you need to specify the feature. You need to select what's the difference between a model which is better than the other model, is basically, of course, the accuracy and the number of features that you have selected. Okay. Right. So this is related to what we are saying at the moment. So there is something called multi-collinearity. Okay, I know it's a big word, but don't worry so much about it. So multi-collinearity is basically when we have a multiple features. Giving the example that we have mentioned, we are trying to predict the car prices, and we have other feature. We have many features, for example, the age, the speed, or things like that. Think about it. We have a multiple feature that are correlated to each other, like very correlated to each other. Say, for example, the speed of the car and the age of the car is really correlated to each other. So in this case, in the very specific situation, we should not use both of the feature because there's a highly correlated feature. And the reason for that is that we have something called overfitting, and we would try to really make sure that our data is not overfitting to the model. Okay, if it's overfitting the model, so the model is not really performing very well. And overfitting, you will see this. You will see this terminology a lot. Overfitting, I'll just give you a quick example. If you do have this kind of data here, you do have the data like that. Okay. Okay, so that's the sort of data that you have got. Okay, and you're trying to like building, like having line between this data. Okay, so the line here can be something like that. Okay, sorry, so the line can be like that. So this sort of line is simply, we can think about this like overfitted to the data itself. So what we're looking at some sort of, like data fitting, such as this one here. Okay, it's the one in the green. Okay, so this is a sort of overfitting the data. Overfitting is, as you can see here, is a model that uses more adjustable parameter than optimal. And this leads us to variation on the algorithm. We'll really talk about it later. One of the problems that we have seen, one of my students is using dataset, for example, image dataset. For example, it was like a self-driving cars dataset, and there is so many data samples for cars itself than other car type, for example, vans or or lorries or whatever. And the interest, for example, the industrial partner, they are really interested on recognizing all vehicle types. But the most type we have is cars, and we have so many samples of this car. And as a result of this, we had we make a model and it's overfitted to the cars because we have so many samples of this. What is the meaning by overfitting in this situation is when you're trying to classify any vehicles, it does automatically mention this is a car. It doesn't mention anything else, even if it's a van or whatever. In this case, we call it the model is overfitting to that kind of sample. So that's not really correct. So there's different ways to simply overcome the overfitting problem. Okay. So few summary of linear regression. So it's find the weights. We need to find the set of weight, the right set of weights, in order to draw our regression line or for our linear function. Okay, so it's a type of parametric learning simply to know the function. Okay, so we have the least square. We've mentioned the least square, the mean square error, and the squared mean square error. So these type of functions or method we use to minimize the values between the y and y hat in our example, in order to fit the best regression line. A major issue that we have is the feature selection. Features means the attributes. In this case, in our case, maybe different attributes. If you're talking about medical data, so the different parameters in the medical. If you're talking about any other problem, such as, for example, car predictions, the specification of the cars, and so on. So the major issue is basically the overfitting problem, and the way one of the ways to overperform it is basically do a regularization. Okay, I don't want you to think it's very complex. I'm trying to simplify things. Okay, so what is regularization? Okay, so regularization is simply it does focus on the most important or most contributing features. So you're thinking this way. So the way we do the regularization model, we including the regularization in our model, is simply the main target or the main aim is to focus on the most important feature. That's the main things. Okay, and the way we do that, I'll just go through. We we're gonna go in a very deep details. The way we do that is that there is something called level L1 regression. We call it lasso L1 regression, or lasso regression, or L1 regression. So we simply encouraging these sparse models in this situation. Okay. And the way we do that is simply, if you recall this term here, so this term here is simply the same as the term in here, which is the MSE, or the mean square error. So this is the MSE. So the mean square error is the one we use to minimize, use the minimization between y and y hat. Okay, so if we gonna split this one here, so this is the MSE. So this is the mean square error. It's not like the back propagation, it's just trying to minimize. So simply it's, to think about it, it's like trying to pushing the weights towards zero if these weights does not have a significant effect on error. Okay, so that's the magic of it. Just thinking it that way. So the W, the weights, pushing it to zero, if the weights of this feature simply does not does not have a significant effect. Okay, so in this case, this is the mean square error. That's the normal mean square error, and this we got here the L1 term. So we just add that term, and the benefits of this term is to simply pushing the weights to zero. So it's only considering the most significant features. Okay, and this is the first way we call it L1 regularization or L1 regression in this particular case. And we have a L2 regression. You will hear about that, which is, we call it rich regression or L2 regression. Again, it shrinks all of the weights a little and simply adds the regularization bound as a penalty. So you can think about it, it's a different way of regularization, but again, the main idea is to simply minimizing the effect of non-importance feature. Again, we have two terms here. So this is the MSE term, the mean square error term, and we have this L2 in this example for range. Okay, so this is the L2 term. So yeah, so the difference between lasso and range, so lasso tends to work well if there are few significant parameters and others are not significant. So if we have a few significant and other non-significant in our data or on our feature, so lasso in this case tend to work well. Ridge, on the other hand, if we have a large parameter or a large number of parameters and they are around the same values, so we normally use the L2 regularization. Question, can we put two of them together? Yes or no? You think about it. Can we put these two regularization techniques together? You think it's possible? Just drop your thoughts on that. Okay. Yeah, actually, I don't think so. All right. So yeah, so basically L1 and L2 can be combined. So we can simply combine the regularization. And combining the regularization, the aim of it is simply to, having the two benefits of these things. If you have, like a different thing. So we basically, it does sometimes work good, work well together. So we can combine these together and it's actually a common way to use. So you can think about it here is that we have this term here is the MSE, mean square error, and we have the first one here is the L1, and then the second one here is the L2, and this is the the modified, we call it the modified loss function or the minimization of the MSE in this kind of case. Okay, so we have the MSE, the mean square error plus the penalty, we call it this L1 and L2 regularization. Okay, so we did combine these two together. Okay, so simply we do have these three techniques or three methods to reduce overfitting. Remember, we're trying to reduce the overfitting. So we have lasso or L1, L2 regularization, or simply we can combine these these two all together. Okay, so this is simple regularization techniques in order to reduce overfitting. So for sometimes in using data science, if you applying for data science, machine learning jobs or whatever, it is one of the common questions that we have. How to prevent your data from overfitting. So the answer is probably regularization is one of the techniques to able to use in order to reduce the overfitting. Okay. So again, another summary of linear regression. We managed to find the weights, and we can use various regularization strategies to simply make our model robust. Going to logistic regression is a little bit acting, it's a very similar way, but it does have a different reason. We use logistic regression is for classification. Remember in the beginning of the session, we have talked about prediction and classification. So logistic regression is mainly used, we use it for classification. So the W is the weights. Okay, the W is what we call it the weights. The weights is simply, if you think about it, if we remember this, draw this line here, we have 1x here. So this is the weights. This is simply the weights. So what's the weights? The weights in order to write the actual or the right line. It's as simple as that. Okay, how to calculate the weights in order to write or fit the best line for our model. Okay. Back to the logistic regression. So again, the classification is mainly used between two classes. Usually it's a Boolean. Boolean, I think you've heard about this Boolean before. Boolean means two things, either 0 or 1. yes or no, true or false. That's normally we call it a Boolean. So that's the classification. We need to classify some certain observation to be either yes or no, 1 or 0, 2 or false, and so on. Okay. Yes. Data points. Yes, the data point. Yeah, we normally, yes, we trying to line the regression line, you know, to fit the data points and the W's or the weights in order to draw this regression line. It's as simple as that. Okay. Okay. Excellent. Right. So, logistic regression. We used a function called sigmoid, this, you know, symbol here, sigma. And we do have, you know, different, just this graph is show you, I'm sure you have been through this before, but this graph just shows you different, you know, different functions. Okay, so we do have something called Boolean. Let's start with the linear function. So linear function is this line here, as you can see here. So this line here is the linear function. Okay, so this one here, this is the linear function, and we have a Boolean step function, which is this one here. So this is the Boolean step function, and this one you can see from its name, it's like a step. And we have logistic functions. Logistic function is such as the red one, the red line, and the blue line, and the green line here. So these are the logistic functions. So this logistic function is, you know, using exponentials on this one, which is not linear functions in this, you know, in this case. Okay, so these are the different types of functions. Okay, so you can think about it. Okay, so in linear regression, we have used a linear function here. For logistic regression or for logistic regression, what are we going to use here? Okay, yeah, it's as simple as that. We're going to use the logistic functions here for our logistic regression. Okay, and we're gonna see in a minute how we're going to use that. So how does it work? So we require in our training, again, in your case, you don't have to worry about that in terms of implementation point of view. So all of these logistic regression, linear regression is just calling some functions to able to perform that on your behalf. But underneath that, underneath the training of the logistic regression, is simply using something called gradient descent to minimize the cost function. As we use the MSE, or the mean square error, to minimize the function for the linear regression. Here for the logistic regression, we use something called gradient descent. Okay. Right, so in terms of the prediction, we simply evaluate the logistic function and used it to determine the item in which class. So we'll do the classification in this example. Right, so we'll start doing the prediction first. We do the prediction, and then we use after doing the prediction, we do the classification, which class we have got. Okay, so in order to classify, simply predict a class, whatever, in terms of, it's either which class for which instance. So simply we look at the sigmoid function, or the logistic function in this case here. And if the probability, if you can think about it, if the function is more than 0.5, so the answer is true, it's in our class. If not, so basically it's not in our class. Okay, I'll just show you the very simple things, and I'm going to show that in a minute. Okay, so you can see here, this is the logistic function here, and see, let's take the red line here. So you see here the 0.5 here, so the 0.5 point here, so 0.5, okay, and simply it's as simple as that. If we have the results of our function, sigmoid function, it's a point, say for example the point is here, okay, so you can see the point here represents 0.2 or 0.2 something. So this lies in the, less than 0.5. So here we can say this is actually a false. Okay. False or zero in this case. Okay. And if I got a point here in the red function, all right, so this is maybe it's almost 0.9%. So this is true or 1. Okay, right, something like that. Okay, so this is as simple as this is the logistic function. So you have here a classifier that we have a threshold here. This is called a threshold here, and anything below the threshold is false or zero. Anything above is true. Okay, so we simply we do that using probability estimate. So we use the probability estimate of the sigmoid for our sigmoid function or our logistic function, and it's 0 if the probability less than 0.5 or 1 if it's more than or equal 0.5. Okay, and so we have the threshold here. So this is simply the logistic regression. And again, it's logistic regression is just like a function. You just to implement, you're fitting the data that you have got, and you just you do the classification using the logistic regression. At this point, anyone has any question so far? Please feel free to unmute your microphone or just drop your question on the chat. Okay. So in order to train our logistic regression, we use. Can you give an example of a type of dataset we could use, either linear or logistic regression? Right. So, for example, just give you an example of a linear regression. This example we just mentioned, for example, the CO2 emission. So the CO2 emission is, like a CO2 emission. You have some, like CO2 values, and you have a temperature values. You simply using the CO2 features kind of things. So the temperature is the dependent variable. The CO2 and other variable, other feature is the the undependent variable, and then you run the regression line. And the linear regression here is able you to predict, for example, in future, if the world CO2 emission has reached that point, like you give alarm, okay, we're going to have that kind of temperature. If we, reduce the CO2 emission by this, this amount, that's going to be reducing the temperature. So you do some analysis why, like the countries and all of that, they say, all right, we would like to reach the net zero, or would like to reduce the CO2 emission to that level. So basically, the global warming or the global temperature, we would like to, sustain it or bring it down, for example. Okay, so that's an example of linear regression. For logistic regression, for example, if we have patient data set and we would like to, you would like to predict or classify if this patient is more likely to have a heart disease in future or not, for example. So it's going to be yes or no. So we can use, in this case, logistic regression to classify this patient. Is it in the area? Is it true that he are more, more can have, like, for example, a heart disease or not, based on the patient data? That's a two, for example, a two example of logistic and linear regression. I hope that makes sense for you. So you have a predefined true amount of logistic. Yeah. Log R cells or none. So if log R, yeah, so we simply use the log values here in this case. So how we train the logistic regression. I don't want to put so much going in much details here, but in this case we simply we need an error function other than MSE. That's we're not using MSE for logistic regression. And for another way, we use the log of LP, which is the probability, and the log of 1 minus B, and simply the cost of the weights again. You know, like if the function like that, so going to be equal to 1. And if 1 minus if log 1 minus probability, so it's basically y equals 0. Okay. All right. Okay. Yeah, I don't want you to go in much details here. I just want you to just know, roughly what's the logistic regression, what's used for, and simply we use use log cost simply to measure the error between our probabilistic in our training models. Okay, so right, so here we're going to move into simply our Colab environment. So I will send you the file here in the chat if you would like to open the file as well. Right. Do you have can't just send it here. Right. I will send you the I'll send you that file later on, so I can't just drop it in the messages here. I will share it in a Google Drive, and I'll send you the link shortly after the session. But looking into the implementation for the linear regression and logistic regression. So first, we've mentioned that all of these things are simply installed, or we can use packages in order to perform our use the functions for supervised learning, such as linear regression and logistic regression. So packages such as Panda, NumPy, Matplot libraries, basically for plotting. Scikit-learn is basically to use this package for like importing regression models from it, such as linear regression and logistic regression. So for example, we load a dataset from scikit-learn datasets. We can load already existing datasets, such as a wine dataset in this case. So we can see here that we loaded the function wine, and this is the feature names, means the attributes of the features. So we use the dataset dot feature names, underscore names to simply, after loading the dataset, to simply visualize the features in this dataset. Then we use the pandas as PD. All of these packages, like Panda, NumPy, Matplotlib, Scikit is very popular, and you will learn about them, and you're going to use them. Pip is basically a Linux installation command to install any package. So we call it pip install and the name of the package. So the name of the package is standard. You should know the name of the package that you would like to import or to call simply to install it in your implementation or your program. Okay. So yeah, here we managed to load the data set and then show the features or the fields of the data set. Then we can use the Panda to simply visualize the data frame, and we can see here this is the data frame and the data. So you can see we have 178 rows with different fields or features. Sometimes we call it features or fields in this data frame. Okay. So the target here is basically the classification, if we're going to use it as a classification. So the target here, we have 3 classes, either 0, 1, or 2. So it can be, I don't know, like the type of wine. I'm not really familiar with it. So it's going to be 0 is like a white wine, 1 is red line, 2 is another type of wine, and so on. So this is what we call it, the target. Okay. And as probably Ian mentioned this morning, that we normally splitting our data set into training and testing. So we have, like some data from, remember we talking about supervised learning. So we have a certain data for training and another data for testing, which is normally unseen data. So normally we, train our model based on the training data set, and we leave the testing part unseen, so we can simply so we can simply use this testing part for testing the model itself and see how the model perform against the testing part. Okay, so here we simply use the scikit-learn to make a model selection to split our dataset into training and testing. And we also imported the metrics in order to use it for evaluating the model itself. And we've called the train test split, and we passed the data and the target, and we've mentioned here the test size 0.3. What's that mean? Can anyone guess what's that mean? The test size equal 0.3? Any guess on that? Right, so simply we mean by that is that, yeah, 30%, we do have 30% testing and then 70% training. Okay, if we need, different splitting, so we can say, for example, 0.2, test size equal 0.2, means that we do have 20% for testing and 80% of the data for training. So you decide the test train split by yourself using this function here. So you don't have to do it. You don't have to do it yourself in this case, right? For the linear regression, again, we do have we call the NB from the NumPy and PLT from the Matplotlib library, and we simply draw this scatter based on the randomized data that we have got. We use the rand function to randomize some data, and this is the scatter plot for X and Y data. Simply we used, again, we imported the linear regression model from the scikit-learn linear models, and then using the regression to get the slope and the intercept for ELAN, for the ELAN matching. So we got the weights. Basically, we would like to get the weights for our linear line. Okay. Then we got the regression model here as a variable, and then we called the linear regression, and simply we fit the model, the linear regression model, with our data, which is X and Y data. Okay, and the X, Y data that we have generated in the top part for as a randomized data. Then we plot the data, it's scattered data, and then when we draw the line, the red line, using the coefficient that we have got from the linear regression. And the results is that we have the scattered data plot and the linear regression, or the regression line in red here. Okay. Logistic regression, don't worry too much about that, but this is actually exactly the same code, part of the code to get the figure that we have just seen. So we have a Boolean step function, a linear function, and logistic functions, and this part of the code which does exactly that. Okay. So using logistic regression, again, we have logistic regression, and we have the CLF, or classification model. Normally we have a CLF, which stands for classification, because this is a classification problem. And we fitting the model by training and X-train and Y-train data, and simply using the scikit-learn metrics to simply predict the model if it's true or not. So remember, we do have a target values. Target values means that we can use the classification. And the accuracy in this case using logistic regression is about 96.3%. So accuracy is basically a metrics, so you can learn about that. So a metrics to compare between, for example, different classification algorithms. You can see, for example, logistic regression, decision tree, random forest. All of these are classification models that you can actually implement it exactly the same data using exactly the same training and testing split, and you see the accuracies for each model, how it looks like. All right, and these are the coefficients, and I think this is for the 3 classes of the wine that we have got. This is the coefficient for first class, the second class, and third class. Okay. Any question? I hope that's not overwhelming for you. Again, I know that some of the stuff you not fully understand, but it's actually giving you like a full, quite overview of the regression model, or supervised learning, supervised machine learning, which is regression model, and logistic regression. Is anyone has any questions? Any question? All right. So again, let's have another maybe. Should we study statistics? No, again, you don't have to study. Don't be overwhelmed about the mathematics, and you don't need to do that. There's no requirements, and you don't need to study statistics at all before starting the course. So yeah, you will get into that without again, you don't need to have a experience to be experienced in mathematics or statistics or anything like that in order to running the course. Even myself as well, nobody like myself, I'm using a very advanced models, deep neural network models, and running, getting results at it, and even modifying the models and making new ones without knowing everything in the background of it and the mathematics inside of it. And nobody knows all of the details of each one of these algorithms, how to exactly work, but overview how it works. That's the important things. Do we need an advanced computer to deal with large data set? So that's a good question. So in theoretically, yes. So but the question is, are you going to deal with a very large data set during your course? I don't think so. You normally the data that you're going to deal with during your course. You're not required to, you know, like to buy a special machine for that. So things such as Colab or Kaggle or whatever, so that's probably enough, or even your machine, you know, like using your own home machine will be enough, will be sufficient. If you're going for like a more advanced projects, we're gonna deal with, you know, normally text has no problem. If you're gonna deal with images mainly, it does require high computational requirements. If you're going to deal with hundreds of thousands of images in this case, so yes, you need to have a computer with a, you know, like a GPU cluster in order to train your model, basically. You would like to use daily data? Yeah, you can within your, you know, like your projects. It's actually normally we put the project within this course. We encourage students to work in the field that you know, the conversion course means that you came from different fields, so you can use your own data, you can use your own problem, for example, to perform or to work in your final year project. Mini project as well as being, you know, connected with the industry, with actual companies, and you know, like solving real problems for them. Yes, I do have. You should have received all of that. All of these things will be received. All the slides, all the all of the collabs as well will be sent to you. I'll make sure that Mariam send you. I don't have all the emails for that, and I can't send it here, but I'll make sure that's being sent. Yeah, if you would like to jump into after that, I will just send the link for the collab in the chat here once I finished. Okay. Any other questions? If not, so yes, excellent. So if not, so we can have another maybe 5-7 minutes break, and we come at 45 to 45 if you're all okay. So I hope next session, try not to make it very long, so we're going to be 30 minutes, something like that. So the hackathon day should finish at 4 o'clock, so we are not over time or anything like that, but yeah. Will we be building a machine learning model for the competition? I think the details of that, Ian will mention that to you. I think it is going to be, yes, it's going to be tomorrow afternoon. So Ian will be introduce you to hack challenges. So the hack challenges is a competition. I think there's going to be group view, which is quite interesting. Happens. I don't have details on that yet, so it's good. Yeah, we'll have the chance to ask about it tomorrow. In the you can see here, you will have tomorrow from 2 o'clock. You will have the introduction to hack challenges. Okay, and the day after that, you're going to have a hack support. Then the announcement on the last day, on the 8th of, oh, sorry, the 11th of August, where some winners will be announced. I think it's the winners including placement opportunities as well. Right. Any other questions? Okay, so thanks very much, everyone, and yeah, looking forward to see you in 5 minutes, so in just 5 minutes. Okay, thank you.